Well, welcome, Florian Neukart, to the Quantum Feedback Loop podcast. I'm really interested to explore the idea of quantum memory matrix with you.
Thank you very much. Thanks for having me.
Maybe you could start off by telling us a little bit about your work with Terra Quantum and what led you to the quantum memory matrix idea.
Yeah, absolutely. So at Terra Quantum, I'm the Chief Technology Officer, and together with many other people responsible for bringing our great research into products. Terra Quantum is broadly defined as a quantum technology company. We are active in all pillars of quantum technology, that is quantum computing, sensing, imaging, and cryptography. And in all of these, we have hard and software development. So depending on the technology, that means different things. For computing, it means, for example, qubit technology, transistor technology. It means a lot of software on algorithms, on hybridization, so how you utilize it. On sensing, and the other ones, it means something else. But generally, I would say my work, also in academia, so I'm also at the University of Leiden in the Netherlands, is at the intersection of quantum information, quantum computing, algorithms, broadly physics. So, but it's really bringing this to life and making products. Now, in terms of the quantum memory matrix, so this is something that generally can be defined as a framework on quantum information and how the universe in general treats quantum information. And there are a couple of questions and reasons why I started working on this. And it's not only me, it's many other people that work on quantum information. And now I think the whole field would be defined as information physics, so where people start to think maybe energy and matter are not the most fundamental aspects. Maybe it's information that is most fundamental to everything. And we can talk about that. I'll get to that in a bit.
Mhm.
But generally, how it all started was with computing. So thinking about the ultimate boundaries of computing in the universe, and then you somehow end up with black holes. So that also comes from my educational background. I studied astrophysics a while ago, but the question that always was interesting to many people and still is interesting is what happens with things that fall into black holes. So for one, we have quantum mechanics that tells us information itself. So quantum information cannot be destroyed. Quantum information, we mean things like the amplitudes that are attached to states, to particles. We mean entanglement. So these things, they cannot be destroyed. But then generally, when you talk black holes, the interesting thing is now things fall in, and Hawking, he calculated and determined that black holes over time evaporate through thermal radiation. So it means thermal radiation is random. All the information, all the things that fall in, they're basically released, but randomly. So it's all gone. And that is a contradiction. So that's called the black hole information paradox. And that's how I started thinking about it. So how could you treat quantum information in a way that it is not lost? So even when the black hole evaporates over time. And that was the first publication a while ago, yeah, where the black hole information paradox was the triggering event, so to say, or the triggering um, um, question for all of this.
Interesting. And so I understand that Stephen Hawking and Leonard Susskind, another famous physicist, had a very famous argument about the loss of information and the idea that the universe always conserves information, that there's a law of conservation of information. And as you explained, Stephen Hawking indicated that information could be lost as it falls into a black hole, although nobody's ever seen information fall into a black hole, I guess. But and then Susskind was very firm in saying that information can never be lost. And I understand the debate between them, which went on for some years, was resolved in part, maybe or in full, by a compromise by Gerard 't Hooft, the Dutch physicist um, who proposed that information is permanently imprinted on the border of a black hole, on the event horizon, the very limit where space-time ends and the black hole starts. Um, do I have that right? And how does that then relate to the idea of storing information in the universe? If it's stored in the border of a black hole, where else is it stored?
Yeah, so that is a good starting point. Yeah, and that also leads to the I would say, to the ultimate boundaries of information storage that is relevant to the whole quantum memory matrix program. Because so interestingly, when you look at a black hole and determine how much information it can store, it actually depends on the surface area. It doesn't depend on the volume. Now, one of the things that we did with quantum memory matrix was to say it's not only imprinted on the boundary on the event horizon of the black hole, it is imprinted in space-time. So we don't only talk about the surface, we talk about space-time as a whole and treat space-time instead of a passive backdrop more as an active information storage and also information processor. So in the usual story, as we said, the information disappears through Hawking radiation. You can define how much information a black hole can hold, determined by the surface area. But then when you think more about other aspects of the universe, about the cosmos, then what or how could information contribute, for example, to dark energy or phenomena like dark matter? So, and this is where it becomes interesting. So, if we now treat the entirety of the cosmos, as being able to hold quantum information, then we find explanation for these as well. So, we can do calculations that show, for example, if information um, contributes to curvature of space-time, and we did that by extending the Einstein field equations by what we call the informational stress energy tensor. If we say information can contribute to the curvature of space-time, and we consider that term in our calculation, then we can see galaxies, for example, despite their rotation curves, can be held together by that additional contribution to gravity or curvature from information. So that would be an explanation for dark matter. I'm not saying that this is the only one, the right one. There's tests that we have to do. And the same holds true for dark energy then. So it's a different perspective on quantum information. So where curvature by information causes these galaxies and unseen gravity, galaxies holding together. There is also, the more information is written, an outward pressure as we see saturation. And that outward pressure, interestingly now, is what we see in various regimes caused by dark energy. So it's a couple of things that you can connect through quantum information. So that's why coming back to the black hole originally, we think that path forward may be promising, and it's so interesting to explore where else information, quantum information, may be a contributing factor. There's more to it, but I'll hand it back to you.
No, that's great. And you raised a number of points that I wanted to explore. I want to explore, I think, mainly what information is,
Mhm.
but maybe before we get to that point, just for the benefit of the listeners and viewers, I guess the idea of space-time and the curvature of space-time has been mentioned, and I think many people have maybe seen, a diagram of space-time as kind of a bendy, curvy fabric, and they might see an image of the Earth, for example, sitting on this fabric and bending the fabric. Um, and so I understand, well, Einstein's famous E equals mc squared is backed by field equations. And the left-hand side of the field equation talks about the curvature of space-time, and the right-hand talks about its relationship to time, and that's where space and time come together. Um, so you mentioned dark energy and dark matter. Dark matter is the force that's, I guess, dark matter is what, 25% of the universe or 20% of the universe? Um, and dark energy is 75%, is that it?
Yes.
Yeah. And so these forces, dark matter is thought to act as a gravitational force to bring galaxies together. And as you mentioned,
Mhm.
the quantum memory matrix theory can explain that. And then dark energy is thought to cause the expansion of the universe. And so maybe if you can just kind of tell us a little bit about different types of curvature and how they can store different types of memory.
So you mean So there is one curvature that we see in space-time, but it's caused by different things. So there is not only one term causing curvature. We have matter, we have energy, but there is one additional term that we now add, which is quantum information. And how I like to treat these, or sometimes talk about it, is memory cells in space-time. And I'll explain why I get to that and the relation to Einstein's equations. So um, when you when you think about the statements that generally summarizes, and I think was it Wheeler who said matter tells spacetime how to curve and curved spacetime tells matter how to move. So that is correct still, but in general relativity, spacetime is smooth. It's continuous. Is described as a manifold, and the quantum memory matrix program generally asks if this manifold, if this smoothness is only an approximation, a large-scale approximation, and if at smaller scales, so near Planck scale, at the smallest physical scale that we understand today, space-time may exist instead of small units of information, so it's discrete. That's not a new idea, so people have thought about this before. But then where the novelty comes in is if we have enormously many of those, and each of those can hold information, then you have, for example, particles moving through space. So the simplest thing that can happen, there is interactions too, especially in a black hole, a lot of interactions. But let's say we have only a particle moving through space time, then what can happen is that we deposit, or the particle deposits quantum information of itself in the space-time cells, and also can create entanglement through the space-time cells. So these space-time cells may itself cause curvature, so to say, by the complexity that's arising, by the quantum information that is deposited into space-time itself. And that is generally a very small term, but on large scales, it can have massive effects. And the more violent a regime is, the more effects it has. So a galaxy per se, I wouldn't say if we look at the galaxy, it's a very violent regime, but there's a lot of mass, a lot of interaction, a lot of energy, a lot of particles. So there's a lot of quantum information written. But a violent regime like a black hole or neutron star mergers, things like that, there's much more quantum information written, and that has then a more massive effect on curvature of the space-time, so by information.
Hmm. And there's so curvature can close things in, but it can also release it. And I think that's maybe what you were referring to with respect to dark matter and dark energy, positive curvature and negative curvature. And maybe if you could just talk a little bit about that in terms of the memory cells that you spoke about. So the idea, I think when you said that space-time, the theory has been that it's or smooth. Maybe that I think of that as continuous, whereas you're saying that it's discrete individual cells. Um, how can these cells get into arrangements where do they form positive and negative curvature, or is it a result of the information that's coming in and out of them that forms this different curvature?
So you have two things. So for one, you have interactions and particles depositing quantum information as things happen in the universe. But then, if a lot of things happen, so the more dense it is, uh, there is a saturation that we can observe. And you can imagine too much information being deposited at one time cannot be held by all of the space-time cells. The storage of each of them is finite, like a qubit in a quantum computer. A qubit in a quantum computer can hold a finite Hilbert space, but it can evolve indefinitely. So there is no limit to how many evolutions, how many changes of that state can happen. But still, the information that it can hold is finite. So now if we think of too much information being available, quantum information has to go somewhere. It cannot disappear because quantum physics tells us it can't be destroyed. So and then it would propagate outward. And there's an interesting work that we've done that goes into the whole universe, into cyclic cosmology too. And again, so I'm also careful to point out many people, especially Penrose, have been doing work on that before on cyclic cosmology. But what we now add is the information again. So if we currently look at our universe at what we understand should be dark matter, what dark energy shows us, then there is a way to calculate backward and forward in time. So backward meaning how fast did it expand in the past? How fast will it expand in the future? Based on the information on things that we see in the universe that will be written, is it more likely that information contributes to a collapse or to an external expansion? And interestingly, what we see now is there are usually these three scenarios how a universe can end. So one is you have accelerated expansion. The second one and most boring one is you have an expansion, but gradual slowdown, infinitesimal slowdown. And the third one is collapse. So, and collapse would then probably mean a cyclic universe, an expansion again. So, and that's what we now can calculate. We can say, based on current math and what we have on data, that the universe will collapse. So there is more information available than outward pressure. So more information causing curvature, causing gravity than outward pressure. So it will collapse. But then, if we assume that information survives a collapse in the next universe, at some point you will end up with too much outward pressure and it cannot collapse anymore. And that's very interesting to see because then all of a sudden you don't only have one end scenario for a universe. If we look over the eons, if we look over the cycles, at some point it will change. At some point from a cyclic universe, it may end up in being a universe that expands and infinitesimally slows down or potentially accelerates. So we don't know.
Mm. Is that sort of along the lines of the Big Bounce theory about the start of the universe? Instead of a Big Bang where all of
Yes.
this energy and matter or information emerges from nothing, that it's just this kind of continuous cycle of expansion and compression.
Yes, absolutely. And so we had another interesting piece. So this whole quantum memory matrix framework, the whole information framework, it grew over the years. And one of the things that we did was also look at primordial black holes. And again, if we assume the same thing, it's always the same thought. If we assume that quantum information can cause curvature of space-time, but now we assume it survives a collapse of a universe. So then when a new universe starts, you already have information wells present. And these information wells, they attract matter. So here you have one way of creating primordial black holes, because right now we don't know if primordial black holes exist. How could they form early in the universe? Because there's not enough matter in one place, so to say, to form those. But if you had already wells in space-time caused by quantum information, they would attract matter and then you could form them early on in the universe, or the universe could form them early on. So that would be another explanation. And I got to be very careful because sometimes you come up with a theory and then you make everything match the theory and fit the theory. That's not what we try to do. So for now, things seem to match nicely, but we'll see. Tests will show.
Indeed. And I want to talk a little bit about the testing later on. Maybe now is a good time to talk about information itself and what's meant by information. You mentioned earlier it's not necessarily energy and mass, like E equals MC squared. It's something else. And I guess I'm trying to get a picture in my mind of exactly what information is in this context and what it is that locks that information in a particular configuration in a cell.
Mhm. So I think the easiest is to think about quantum computers. So how a quantum bit works and how information is associated. So quantum information is generally the information contained in a quantum state. But if we think about the simplest one, the bit still in a computational basis is 0 or 1 when I look at it, when I measure it. But then you have the amplitudes. So the amplitudes is the probabilities generally. So it's a little more, you got to square them, but the probabilities when you measure the system uh, of the system collapsing either into 0 or 1. Say I have 60% of it collapsing into 1, 40% collapsing into 0. That is quantum information. The probability amplitudes, not the 1 and the 0, is the amplitudes. Now, if you have more qubits, then things become even more interesting. So because you want to have interactions, you entangle them. If I do something to that qubit, it affects that qubit. And how does it affect it? It affects again the amplitudes. So that is the next one, the entanglement. So that is also quantum information. So it can be stored in superpositions, entanglement, correlations between systems. That's what we mean by quantum information. And then you have in quantum physics, the conservation of information, which is also connected to unitarity. So if a system is closed and evolves according to quantum mechanics, it cannot be destroyed. It can become scrambled. That's what we also recently did with one of the black hole publications, where we say there's entanglement present and information flux at the horizons of black holes. They can become scrambled, it can become inaccessible, but is not gone. And that is very important. Generally, that's why black holes are so important and why we're interested. But I hope that conveys somehow what quantum information is. It's not something that is easy to grasp because when we think about the bit, I know we have one and zero, but then you know how it works.
Yeah, yeah, and I think that's important for listeners and viewers to understand, I guess, is that the computer bit itself has just two possible states, right? Zero or one.
Yes,
Whereas the power of quantum computing in the qubit is that it could be in any range of states, I guess, between zero and one, correct? And when you
absolutely.
talk about amplitudes, I'm imagining um, kind of you mentioned the probability of the state being, in this particular position between zero and one versus this other position between zero and one, I guess that's what I'm thinking about. And I guess if we have that image in mind, then I guess, yeah, I guess and the connections between those qubits, I think it becomes clearer. Yeah, the idea of information being a particular configuration of quantum states, maybe something like that.
Yeah.
Yeah.
So and that's one of the things that I haven't mentioned here, right? So the amplitudes, when I say each state has an amplitude associated, so and when we look at it, when we measure it, then it becomes one state. So the superposition is one of the powerful effects that we see in quantum physics that allows us to do these powerful computations. A state in a quantum computer having many qubits or a quantum computer can have all configurations that it can represent exist in one time. And that is so one of the reasons where the remarkable power comes from. If you do it right, you only have to look once for going through all the complex configurations of that system, potentially solutions to your problem, and get your information out. Now, in the quantum memory matrix, in the space-time idea, if we carry that on, then information is stored through local imprints. So what we did is also define a mathematical operator or operators, so imprint and retrieval operators, because we can not only write, we can also retrieve. And with we, I mean any interaction, any particle that propagates through space-time can retrieve information too. So when a particle um, interacts with a space-time cell. So the space-time cells, we now think about the space-time as sort of a grid, then the cell is updated. And this update is also unitary. So like in quantum computing, like in quantum physics in general, which means in principle, it's reversible. And here again, I must be careful because the question I got already was, does that mean we can reverse time? We can't. So because it's too complex interactions. But generally, quantum physics is reversible. Do it twice and you get the original configuration back. So you could more likely think of it as a swap of quantum information. So you have one particle that has quantum information associated with it. You have the space-time cells that also have quantum information. And part of the quantum state of that particle is transferred into the register. But it's not copied because if it was copied, we would again violate one of the quantum physics principles, which is a no cloning theorem. We cannot copy. But the information now becomes distributed between the original system and the cell. Um, and that is important. So they have now a connection, so to say. And a later interaction with some other particle with that cell from another particle can undo that. So can override it, so to say. And that is important. In a black hole context, it's mildly different. Um, so we have the imprints near the horizon that we see. Um, but the outgoing Hawking light radiation can interact with these imprints, and they can gradually pick up these correlations, and that's how we can say there is information left and it doesn't vanish. Um, Locally, it may look thermalized, which is what we expect from Hawking radiation, but globally, it has evolved into a more complex quantum state that still has structure. So that's where the information goes. It's not gone.
Mm. That's fascinating to think of as you describe the information swapping between particles and the cells, and mentioning that it's never copying, it's always just exchanging information. So I guess if we think of information as essentially a set of probabilities, when you talk about writing and retrieving in the cells, it's writing and retrieving essentially probabilities, is it?
Yes. So probability, yes, the amplitudes, there is always more to it, so mathematically, but yes. And there is more than probabilities. There is correlation, so entanglement, that is also quantum information. So it's more than just one thing.
And if one cell is changed in the swapping process, does every other cell change?
So that depends on how much information is written. So if we have cells being entangled through some previous interactions, then yes. So if you do something to one cell, it would then also affect all the entangled cells that are connected to it. Now, if we think about violent regimes where we have um, too much information at once, so where we have to propagate that outward, um, then again, it's a mildly different story, but here too, yeah, you would affect everything in the vicinity. But this is what we would then perceive as dark energy. And interestingly, so it also would explain why we would see different dark energy values in different regimes of space-time. So it's not always the same. It's not just one value. It mildly differs depending on where you are and what happens.
Hmm. That's interesting. Actually, we've written recently about the debate, I guess, whether dark energy is a constant or whether it's variable. And I guess information is coming out to support both ideas.
Yes.
Uh, but
Yeah.
your idea that the cells are locally entangled could cause differences, like locally connected.
Yes. They're locally connected, and you could say so a change in one cell can affect neighboring cells through these interactions and correlations, and over time, information spreads. So it can spread, scramble, can become part of a larger correlation structure, like with the black hole, like we said before, but there is no instantaneous update of the entire universe. So that doesn't happen.
Hmm.
And it's a very important thing because we also with quantum physics and generally also with QMM, we don't want to violate causality. So there's yeah.
Yeah. Cause always before effect, I guess.
Yes.
Yeah. Um,
Yeah.
and I guess maybe just to talk a little bit about that. So that's, I guess, maybe a little bit about the second law of thermodynamics,
Mhm.
um, which is a bedrock principle, I understand, of physics that time only goes one way. Um, there's talk about the second law of information, and I'm wondering if you can just explain for us what the second law of information says, and does it relate to the second law of thermodynamics?
Yes, it does. Yeah. Yeah, that was one of the other interesting works that we did. Um, so I always say interesting because it's interesting to me. I hope it's also interesting to the listeners. But so one of the things that we looked at was the second law. Yeah. And so it's about, as you said, it's about energy conservation. Energy can change form, but the total energy of a closed system, also the total energy of the universe is conserved. All of the energy that anybody will ever use, it's already there. So it cannot be created, cannot be destroyed. And now the second law of, but we didn't give it a name, but we just said the second informational law, so should extend that one, but extends it to space-time itself. So it proposes that entropy production, which we see anyways, and information flow are connected to curvature. Entropy, so very important in thermodynamics, just means disorder generally increases over time. That would be one of the ways how you can look at time, the entropic era of time. So the usual example that people give is you have your coffee cup here, you drop it, it breaks, but it doesn't jump back up. And assemble itself again, because that would require more energy. It has to come from somewhere. But generally, what we see is we see more disorder over time. And the informational second law says now entropy production and information flow are connected to curvature. So there's also another work that we did where we showed that generally quantum information and curvature um, there is a duality that exists. So that connects to this one, but it just means it's the same thing through a different lens. Uh, so the geometry, or say gravity through geometry and gravity through information. So it's this duality that we found. So that means curvature generally can be interpreted as a geometric expression of information flow or entropy production. So if entropy is produced, we also have information flow, and that means we have curvature that emerges. And it doesn't violate the first law, so we don't generate energy. It's exchanged between matter. So energy is exchanged between matter and radiation, but the local system remains conserved. And this exchange happens through the space-time cells, so the quantum memory matrix cells that we defined. So it's generally a microscopic, the smallest on the Planck scale, a microscopic foundation for the second law. So we have now information that can make the second law emerge. So local entropy grows because information becomes distributed through correlations in the quantum memory matrix in the space-time. So that's how it connects. That was a lengthy
Yeah.
explanation. I hope that was more or less clear, but in general, the idea is always the same. You have your network of cells, or we have our network of cells, and we write quantum information that causes some effects, amongst others, the curvature contributes entropy production. So therefore, we can describe this one thing using the other. It's just the quantum information is more fundamental.
Hmm. Yeah, fascinating. So the idea that the geometry of the curvature tells us something about the information that's contained.
Yes,
Yeah. Yeah. Okay.
it does. Yeah. So you can
Yeah.
derive the amount of information that is contained in a region of space-time by the curvature. Because now we know that curvature and information is the same thing. So we look at gravity. Gravity actually is what we have here on top, but the duality that we have is quantum information and curvature. So you can express one using the other.
Hmm. And so yeah, I guess so we've had a fascinating kind of exploration, I guess, of the idea of space-time and curvature and information. And I think you've said in the quantum memory matrix theory that information could really be the most fundamental aspect of the universe. And just for people trying to grasp that, because our daily existence, our five senses tell us that energy and mass are the fundamental parts of the universe. And I'm just wondering how we could envision in a way that would relate to our senses or override our senses, how information could be more fundamental than the physical stuff that we see all around us.
Hmm. So I wouldn't say so. Matter is real. I would start with that. And but what physics has taught us, and that depends when once you get in or when you get in touch with quantum physics, but taught us that matter is not what the senses suggest. So you have this description of there's different interpretations, but so one interpretation of quantum mechanics says reality doesn't exist until I look. So there are Schrodinger's cat and whatnot.
Yeah.
But generally, that would mean I have to, or there has to be some interaction, some photon hitting an electron to force it in a spin state, for example. So a particle is not a tiny ball, a tiny classical ball. It's an excitation of quantum fields. So that's what we know. And the behavior is described as we had before by the amplitudes, by quantum states, phases, correlations. And when I'm very careful. So when I say information is fundamental, I don't want to say that matter is an illusion. It just means that matter is a stable expression of a deeper quantum information structure. So, and that per se, that statement may not be news. It may be mildly differently said, but that's what generally also quantum mechanics, depending on the interpretation that you follow, also says when you say until I look, um, there is uh, no stable state. So look doesn't mean the human looking; it means some interaction. But um, in quantum information, I think the last thing I want to say is that information is not a metaphor. So it is really something that we can measure. It is something that is there. We know it from other quantum systems, from simpler one, quantum computers, sensing systems. So all the quantum physics that we do, but it's important that we have distinguishable quantum states and correlations. And matter may be what information, maybe what uh, information looks when it becomes stable, local and measurable. Maybe that's it.
Yeah, and fascinating because I'm thinking it brings to mind the idea again of information being expressible geometrically. Um, Maybe the information is sort of the form or the geometric shaping of the matter. Is that a way to think of it?
So not the shape of the matter itself, I would say, so the shape of space-time, yes. But then, I mean, when you, and again, we can go into different directions now, but when you think of chemistry, and how the quantum states of electrons influence the binding of molecules, so this is something that matters. In that sense, yeah, what forms is based on quantum mechanics, and then in the end can be described by quantum information because that's all there is. So the information describing the states and then the probabilities that we get of states ending up in one or the other configuration, and then that also resulting in molecular properties. So in some sense, yes, but I wouldn't say it shapes it. Yeah.
Right. Okay. Yeah, no, I understand that it makes sense, I guess, at the molecular level in
Mhm.
any event. Yeah. Um, So how could quantum memory matrix theory be tested, or has it been tested? I'm wondering about, new instruments like the DESI, the dark energy probe that's looking at the expansion of the universe, for example. Whether is there experiments that are kind of looking at your idea, or are there planned experiments?
Yeah, we have thought about a few, and one of the things that will be very interesting is the next generation Event Horizon telescope. Um, the original one, I mean, it does the same thing, but the original one didn't have enough or good enough resolution, angular resolution, to look closely enough at the photon rings. So when you look at a black hole, you have all seen these images that were generated, right? The black hole in the middle and the swirling photon rings. So you have infalling matter that heats up, that emits radiation, and it's a violent regime, so high curvature regime. Now, if we have that informational contribution to gravity, to curvature, the photon ring displacement will look mildly different than with the current theory that we have. So we can do both calculations. We can observe, we can calculate what it's supposed to look like without informational stress energy transfer, and then we calculate what it would look like with informational stress energy transfer. And if the last one is a match, then there's a pretty good indication that information indeed is deposited in space-time and contributes to curvature.
Wow. Yeah, and I mean, it was only a few years ago, I think, that the Event Horizon Telescope produced that famous picture of
Yes,
the black hole with the
very
ring.
exciting, yeah.
Yeah, and so that was an array of, as I understand, an array of telescopes around the world. I can't remember how many, like a dozen or something like that, that combined their images into one to produce a composite image of the black hole. Is that the case?
Yes,
Yeah. And they were looking at the black hole that's at the center of the Milky Way, right? The Sagittarius A star.
yes.
And every galaxy pretty much has a black hole at its middle.
Yes, as far as it's currently understood,
Yeah.
yeah, you have black holes. So there are different names for it. Quasar, for example, would just be a black hole where there's a lot of infalling matter and heated up, and it's brighter than the brightest stars. But yes, so every galaxy has some strong gravitational source that it holds together, that holds it
And
together. Uh,
and so the new version of the Event Horizon Telescope, when is it scheduled to come online?
So I hope in 2028, but we'll see. I'm not updated on the latest dates. So last time I read about it, I saw it was supposed to be 2028. Yeah,
Yeah.
so it
Yeah.
would be very exciting.
Yeah, for
Um,
sure. Yeah.
there are different things that we can look at. So one of the things that we are just working on right now is looking at the cosmic microwave background. And if there is an information signal in the cosmic microwave background. So we use mostly data that was collected by Planck satellites. But so the challenge here is that the signal most likely would be under the error threshold. So very difficult to extract. We have some indications. So usually you talk of a signal validation strength of 3 sigma that would say this is confirmed. There is a signal. We're now with our current analysis at 2.75. So there is a signal, and we hope we can get better and extract better results. But this is what we're messing around with right now.
Wow. Well, so yeah, in the cosmic microwave background, that I understand that's kind of like a impenetrable layer of plasma, I guess, that exists. We can look back, I think it's what, the first 300,000 years of the universe?
Yes, it's
Eh,
the
Yeah.
yeah.
And so you're looking at the signals or the um, was it like radio signals or something coming from the cosmic microwave background?
It's a microwave, yeah. And so what we're looking at is if we can extract in various locations of the CMB some signal that we could interpret as quantum information having been imprinted in the past by violent events or by violent regimes, black holes, for example. So if we can observe that in multiple places, if we can identify it reliably, then we could argue that in the cosmic microwave background, even we see that quantum information has been imprinted throughout the history of the universe. So it would be even more interesting, but that if we think about looking for life. So I'm also affiliated with SETI Institute, and they are very interested in many things. But so if you had, for example, a civilization in the past that could form enormous structures for energy conversion. So, for example, a Dyson sphere on the star, even more massive ones. So there might be some techno signatures that you could find. But again, this must be high energy. So it's not just us being on the planet here. That wouldn't be enough. So it must really go beyond our current capabilities. And maybe there was something in the past, maybe not. But it would also be something that you could look into.
Wow. So looking at it really from both ends, from the beginning in the microwave background and the black hole where space-time ends, I guess is yeah, really, really fascinating to th and to think too that maybe as early as 2028 we'll start to see some evidence, as you said, of the displacement of the photon rings around the black hole that might give some
I
information.
would hope so, yeah. We'll
Yeah.
see.
This has been a really fascinating kind of imagining of space-time and maybe ways that people have never thought of before. And just, I guess, maybe to kind of summarize or wrap up what we've been talking about, I'm wondering where this leads to, like where, if proven or if improved, where the quantum memory matrix theory takes us, maybe practically speaking, or the next steps of scientific discovery. Does it affect, for example, quantum computing?
Yes, it does. It has already. So one of the things that we did was um, so we tried to experiment and say, so if let's assume our quantum computer, the simple ones that we have today, um, they are space-time. Each qubit is a cell, a quantum memory matrix cell. Could we, in theory, in principle, reproduce this mechanism that we described for imprinting and retrieval of information by simulating a particle going through? Um, Simplest experiments just does that. Yes, we could, but that was no surprise. But then the next question was, so the universe usually is very noisy. So if other things happen, if there is noise, if there is interaction, can we still do it? And can we retrieve the information back if we simulate a particle? And it turns out we can. So and now all of this led to a very nice error suppression method, mitigation in the end. So the idea then being, so quantum computers being noisy. So we just assume or make this connection. The universe is noisy, so quantum computers are noisy. Can I retrieve the information in a way that ignores the noise at all completely? And there is now ways to do it. And we built that actually into our platform in our quantum computing software already. So let's assume some customer shows up with an arbitrary quantum algorithm, a quantum circuit, says, this is too noisy. With the current machines, I cannot get meaningful results. Can we improve upon it? So in our system, we'll analyze the algorithm and then bring in layers of QMM suppression and then improve ideally the output quality or reduce at least the number of qubits. So what we saw in our experiments is that we can reduce the qubit count for a noisy algorithm by about 35 to 40%, which is very nice in today's regimes where you want to have every single qubit that you can get. So it has an impact here already. Maybe there is more to come in terms of technology. I would assume so. So the more we understand about how information is held in nature, quantum information is held in nature, I'm sure the more it will help us to make better quantum computers.
Yeah, and the big problem, I guess, with quantum computers now is the circuits disconnecting, decohering, that the connections between the qubits disconnecting. So you're talking about QMM as a way of getting around this problem of the noise that causes these disconnections.
Yes. So basically what it does is um, so you have processing happening, and as you evolve, so that's how you what you say when you go through a sequence of quantum gates. So as time moves on, you evolve your state. You have your input state, you apply gates, and then the more gates you apply, uh, the more noisy it becomes. So that means the more likely it is that the result that I get at the end when I measure the system is not what I expect it to be. So now if we introduce one layer of QMM retrieval, then it extracts information. So very basically, it extracts information that is useful to the state and propagates only that one forward. So in the end, we got rid of the error while the processing happened. And that's what we do a couple of times. And the goal would be that I have a high quality state from the beginning to the end. So and then when I measure the system, I get more likely the result that I want to see versus that I don't want to see. And I say more likely is because a quantum computer, even if it's perfect, is still a probabilistic system. It's always a probabilistic system. So you will never be able to eliminate all the probabilities of configurations that you do not like. You may still get one that you do not like. So that's why you usually do a readout 1,000 times, not only once. And then you get 800 times. Matching result 200 times is some random results.
Well, and that's when the power of the quantum computer really will, I think, affect the world. And that's one thing that we just continually look at is it seems that there's developments almost every week on this question of the error correction, and it seems like it's getting closer and closer. Just maybe one last question on this is quantum quantum computer memory itself. Do the memory cells hold any promise for developing a memory for something like a quantum internet? As signals exchange and need to be stored between machines?
So it could be. I don't want to say no. Um, so if we so let's think about quantum networks in general. So if we want to distribute, that's what we do. We want to distribute, preserve, and recover quantum information. So in that sense, the more we understand about how the universe does it, the more understanding we will be able to gain for that as well. So in spirit, I think it's very close to the quantum memory matrix idea, which is preservation of information and propagating information through a network of cells. So in that sense, yes, but it's not something that I have thought about in detail, or we have, but potentially, yeah, it could contribute. Um, it contribute, yeah.
Mhm. Well, I mean, you've taken us through a really fascinating journey of space time and imagining all the potentials, I guess. And so this is something that we'll definitely want to see how it develops. And we'll be following the new Event Horizon Telescope and see where that takes things. So I want to thank you very much, Florian, for your time and for this great discussion. We would look forward to talking with you soon again.
Thank you so much. It was very nice talking to